Alright, so in this particular kinematics video, we have a car that starts at rest, as stated in the problem, and is going to travel 100 meters to the right. And as it's doing that, it is accelerating at a constant rate of 2 meters per second square towards the forward direction, or east. Okay, alright, so let's do it. Here's A, B, C, D, E, F, G. Pause the video, read it. Alright, let's go ahead and tag it. Part A asks you to find instantaneous speed at 5.75 seconds. To find instantaneous speed, it is the same as to find instantaneous velocity, except when you present your answer, you don't need to include a direction because instantaneous speed is a scalar quantity. The easiest way to do part A is just to use this kinematics equation for final velocity. Final velocity is equal to A times change in time plus the initial velocity. But in this particular case, the car starts at rest. So I will go ahead and cross that out. My acceleration is given as 2 meters per second square. The time here is 5.75 seconds. So if I just plug those two values in, I'm done with part A. So the instantaneous speed at exactly 5.75 seconds is 11.5 meters per second. So that'd be my answer. So again, you can use the final velocity function to find instantaneous speed. It's just when you present your final answer, do not include a direction. All right, so that's that. Part B asks you to find the change in velocity during the interval of 4.4 to 7.3. So on the screen here, I simply just apply the average acceleration equation. The reason I do that is because it's asking for the change in velocity. So delta V is in my average acceleration equation. So here, I said for delta V, I will keep delta V as condensed as is. So to get delta V by itself, I will multiply both sides by delta T to get rid of this delta T in the denominator. Multiplying both sides by delta T will give you a delta T is equal to change in velocity. Well, we know our acceleration is 2 meters per second squared because that was given. The change in time here is 2.9. So if you watch towards the top right of the cursor here, from 4.4 to 7.3 is a difference of 2.9 seconds. So that's where the 2.9 seconds come from. So make sure you pay attention to your initial time and your ending time in these kinematics problems. All right, so that's where the 2.9 comes from. Calculator work, 2 times 2.9 is 5.8, and the unit here is meters per second. And since it asked for change in velocity and it didn't use the word magnitude or anything like that, I'm going to go ahead and include direction. In this case, that's east based on the diagram. The car's moving to the right, or you can put a plus sign, or you can put forward, but indicate some sort of direction. All right, so that is our answer for change in velocity. Let's do part C. Okay, part C asks us how long does it take to cover the 100 meters. This one is pretty straightforward. I think the easiest way to do this one is just use your displacement function. Why? Because VI is 0. You know your delta x is 100 meters. You know your A. The only variable missing is the time, which is what you're asked to find. Okay. So in that case, all we have to do is get t squared by itself. In doing so, the 1/2 and the 2 cancels out. 1/2 times 2 is just 1. So that leaves us with just t squared on the right side of the equal sign. And on the left side, we have 100. If you pay attention to units, this is second squared because the meters on the left side will cancel out with the meters on the right side. And then to solve for t squared, we have to move this second square. And this is just a unit. It's not a variable. Second square up to the top left, which leaves us with 100 second squared. But again, if all of the units are proper, you don't even have to worry about writing units out as you do scratch work because it'll always cancel out on point. Okay. All right. So therefore, to get t by itself, we square root both sides. Square rooting the right side, can't take out the exponent there. And then the square root of 100 is just simply 10. So that's your answer for part C. So it would take 10 seconds to cover the first 100 meters shown in the diagram there. Okay. Now, what if you wanted to use a different strategy? Okay. These kinematics equations are pretty cool. It all depends on how your brain sees these problems and how your brain wants to tackle these problems. I can use the average velocity function, which is delta x over delta t, but then I can also set that equal to the other average velocity function under constant acceleration, which is vf plus vi divided by 2. Or you can write vi plus vf, it doesn't really matter. Okay. So here we're trying to solve for delta t. Delta t is initially in the denominator, so I'm going to flip the whole function upside down just to get delta t in the numerator. By doing so, I'll flip the left side, which brings delta t up, brings delta x down. On the right side, brings the 2 up, it brings the vf and the vi down. Here, to get delta t by itself, the next algebraic step would be to multiply both sides by delta x. Right? Because right here it says delta x divided by, delta t divided by delta x. This is a division, so to get rid of delta x, you need to do the opposite operation, which is to multiply both sides by delta x. So that'll give us something that looks like this in my next line. Well, here we know vi is 0 because it starts at rest, and therefore all we have to do is figure out the final velocity. Okay, we know delta x already. We know delta x is 100. The only thing that's kind of holding you back if you decided to go with the strategy is the final velocity. How fast is the car moving by the time it reaches 100 meters? And that's easy to find. We can use our other kinematics equation, which does not have a t. Why? Because we don't know what t is. That's what we're trying to find. Vi cancels out, and therefore vf square is simply equal to 2. The a is 2. Delta x is 100 because this particular part cs is the time that it takes to cover the whole entire 100 meters. So as you can see here, it's just plug and chuck now. 2 times 2 is 4, 4 times 100 is 400. So vf square is equal to 400. But to find vf, you have to take the square root of both sides. So therefore, the square root of 400 would just give you 20, not 200, 20. Square root of 400 is just 20, okay? Therefore, we know this value there, so all we have to do is plug it back in. So therefore, in the numerator, the 2 gets carried down. VF is now substituted for 20 meters per second because I just calculated that. And then delta x here is 100 because the problem wants to go from 0 meter to 100 meters. So if you simplify this, 2 times 100 is 200. 200 divided by 20 is just 10. So as you can see, it doesn't really matter which method you choose. You should get the same answer. And this will hopefully build confidence as well. All right, let's do part D, E, and F. Part D asks us to find the time it takes to cover the first 50 meters. So the first 50 meters, this right here in the green that just came up, okay? So as you practice, know what part and know where in the motion is asking you to calculate. So it says the first 50, so it's gonna go from 0 to 50. Therefore, how long does it take? Well, if I start back at 0, there's important information that I know. I know my VI is 0 for this particular problem because it says a car starts at rest. So therefore VI is 0. I'll cross that term out. Delta X I know. It says the first 50, so delta X is just 50. And then the 2 represents acceleration, so I plug that in. So the only thing here in the statement is t squared. Again, it just happens to be this for this particular problem. The acceleration is 2, so it cancels out with the 1/2 nicely, but it doesn't have to. So just kind of go with the flow. And then therefore we have 50 equals to t squared. To get t by itself, square root both sides. Therefore, the square root of 50 would just be 7.1 seconds, about 7.1. Okay, so that'd be your answer for part D. All right, we can use the same strategy here to do part E. Part E asks you to find the time it takes to cover the first 25 meters. So let's knock this out, and then I'll point out some things you should be paying attention to. All right, so here's the first 25. I just kind of eyeball it there. That blue arrow is about halfway from 0 to 50, so it doesn't really matter. I'm just trying to teach you how to do physics here. VI cancels out again because the blue arrow or the blue line that I have here starts from 0 meters, which implies that it starts at rest. Okay, and then delta x is just 25 because it says the first 25 meters. 1/2 gets carried down. A is 2. T squared is unknown again. And then the 1/2 and the 2 cancels out nicely for this problem. We have 25 is equal to t squared. And then to get t by itself, square root both sides. Square root of 25 would give you a time of 5. Okay. What I do want to point out is this. Kids often have misconception about motion. Okay. We know that it takes 10 seconds to cover 100. So sometimes, because kids don't understand what happens when a car or an object accelerates, that when they ask for the time to cover the first 50, kids will often just take 10 and divide it by 2 because it's half the distance. And that's a big no-no. Okay, so that's a big misconception. So I hope you're listening to this part right. Do not just take the time that you found for the 100 meters and divide it by 2 simply because the problem asks you how much time it takes to cover the first 50. That is a big no-no. The answer is bigger than half of the time, because as the car starts to accelerate, it's starting to pick up speed. It's starting to get faster and faster and faster and faster. So during the first 50 meters, it takes more time to get up to speed, which would imply it takes more time to cover that first half of the distance. Now, once the car gets to the 50-meter mark, it keeps on getting faster and faster and faster and faster and faster and faster. So therefore, to cover the next 50 meters or the last 50 meters, it actually takes less time because it's now getting even faster and faster and faster. So when you're moving faster, it takes less time to cover the same amount of distance, okay? So don't just think linearly. You have to think, in this particular case, quadratically, because this t square in the displacement function is a quadratic function. All right. Likewise with this blue arrow, sometimes kids will just take 10 and they'll divide it by 4, and that's illegal. That's not proper for this particular problem. We found that it actually takes 5 seconds to just cover the first 25, not a fourth. Okay. It takes half the time because you are barely picking up speed. You're moving kind of slow. You're getting a little faster. You're getting a little faster. So it actually takes you quite a bit of time to cover this first 25 meters. Okay. So think slow, slow, getting faster, getting faster, getting faster, getting faster, getting faster, getting super fast, getting super fast. So therefore, it takes less time and less time to cover, the following distance. All right. Listen to that again. If it doesn't make sense, see me. All right. So here we go. Therefore, the part F asks you how long does it take to cover the last 50 meters. Well, to cover the last 50 meters, we kind of know the answer already here, right? We've already found that it takes 10 seconds to cover the full 100. We know that it takes 7.1 seconds to cover, the first 50. So, well, it already took 7.1 seconds to get to here, the 50-meter mark, and then it takes only 10 seconds to get the whole thing. So we know that it would take about 2.9 seconds to get from 50 to 100. But I'll show you how to do this properly, assuming you weren't asked part D and E. Like you would just ask part F straight out. Okay. So to do this properly, from the get-go, delta x here is 50 because from 50 to 100, it says the last 50 meters. So that would imply that you start from 50 meters and you go to 100 meters. So the displacement there is a positive 50, but I'm just going to leave the positive sign out because I'm just doing calculator work here. What I do want to point out is this right here, the VI. At the 50-meter mark, the car is already moving. Okay, so do not plug in VI as 0. So it is essential, it's vital that you pay attention to where the problem starts. This part F here starts at 50 meters. So the car is actually already moving at some velocity. I don't know what it is, but I know it's moving. Because I know it's moving, I cannot cross out VIT. VI is only 0 all the way back at the beginning of the problem where xi is equal to 0. So don't make these rookies mistake. So you notice here, I didn't cross VI out like I did in the last couple of parts. I left that as VI and I highlighted for you. Okay, I need to find what it is. So I know that if I use the information from beginning to 50, I can find what my final velocity is. But my final velocity now becomes my initial from 50 to 100. So this is like a key concept to apply. Okay, I want to say it again. I can use the information from 0 meters all the way to the first 50. I can find that final velocity. But that final velocity now becomes my initial from 50 meters to 100 meters. So I'm going to crank it out. I want to use this common form, which has no time. I want to cross VI out because, again, I'm starting from 0. I'm trying to figure out how fast is the car moving by the time it gets to the 50-meter mark, which will be my initial in my work. So the only thing missing is just VF. I know my A is 2. I know my delta X is 50 because from 0 to 50 is 50. And I can figure out what that is. So therefore, VF is just the square root of 200. 2 times 2 is 4. 4 times 50 is 200. So the square root of 200 would be about 14.1. Okay, so you notice here, I solved for VF, but this VF is the VF of the first 50 meters. But this problem starts from 50 to 100, so therefore the VF now becomes my initial velocity for the second half of the distance. So if you plug that in, the 1/2 and the 2 cancels out, and let's just carry it down. Here, VI is 14.1. I kept that t down, and then the 1/2 times 2 is just 1, which is just t squared. And then here I just carry down the 50. I left the units out just to show that this is a quadratic function, okay? So if you've seen my other videos, when you get to here, you notice here you have a t square, okay? Here, let me take that out. You have a t square, you have a t, and you have some coefficient. So you got to start recognizing this is a quadratic function. So therefore, to find time using this, you can do long, tedious work on your paper, or I would just like to use a quadratic solver, which I hope your calculator has for you. And if you don't, then update your calculator so that you can get these tasks done quickly, okay? All right, so in order to use quadratic function, you need to set the whole function equal to 0. So here I have a 50 on the left side. I need to make the whole function equal to 0, so I need to move this positive 50 to the right side of the equal sign. Moving the 50 changes sign, so it becomes negative 50. And I just rearrange it so that it looks like a quadratic function. We always write the variable with the highest exponent first. In this case, is t squared plus 14.1t, which is the next variable, and the exponent here is just 1, right? But we don't write the 1. And then minus the 50. The 50 doesn't have a t, so it's the last one on the list here. Why do we do that? We do that because we need to figure out what our coefficients are. Here for the t squared term, there's no number in the front because there's no number. The number is a 1. We don't write 1 times t squared, we just write t squared. So it's accepted that the coefficient in front of t squared is a 1. B is 14.1. It's a plus 14.1 because there's a plus sign in front. So I just wrote 14.1. And then C is negative 50. And again, you have to learn to see the symbol in front of these coefficients. Sometimes kids just write 50 because they only look at the number. And I would say, look at the sign in front of the coefficient as well. So in this case, your C value is negative 50. Okay, so now to solve for this using this method, I need to use a quadratic solver. So I'm just going to go ahead and use a quadratic solver here. I have it loaded. So here, my coefficient for A is 1. My coefficient for B is 1.41. Oh, no, excuse me, 14.1. Whoopsie. 14.1. And then my C is negative 50. And if I hit calculate, I get an answer of 2.935 seconds. Okay. The negative answer, I don't care here. X represents my time, and time cannot be negative. So when you do quadratic, you should always get 2 answers. The question is, which one do you pick? In this one, I would pick the 2.93. 1, it makes sense. 2, it's the positive answer, and time is a scalar. Okay, so let me go back to this. So therefore, if you do all this correctly, you should get an answer of 2.9, which is consistent with the last 2 answers, right? Again, as I stated earlier, we already know the answer for this is about 2.9 because we found the time to cover the first 50 already, and then we also found the time to cover the whole 100. So really, 7.1 to 10 is a difference in 2.9 about. Okay, but the work that I just presented is how you would do it properly. Hopefully, if I can free response questions, stuff like that. All right, now let's do the next slide. That's part F. Let's do part G, and I think that's the last part for this one. Okay. All right. Okay, so again, time here is 2.9 seconds or 2.935, whatever you want to run to. Part G. Part G asks us to calculate the average speed between 30 to 70 meters. So here in my diagram, I kind of eyeball it. There's about 30, there's about 70. So let's knock it out. Average speed can be calculated using the average velocity function here. The car is going one way, so all I have to do is use the average velocity function. But at the end of the day, when I give my answer, I just leave out the direction. So to find average velocity, I do initial plus final or final plus initial here. I've just chosen to write VI plus VF because it starts at 30, which will be my initial, and I'm going to add it to my final divided by 2. All right. But I don't know how fast the car is going at 30. I don't know how fast the car is going at 70, which is okay. Super easy work, okay? All you have to do, again, is use this particular function, VF squared minus VI squared equals 2A delta X. I'm going to start from 0 to 30, okay? Because I start from 0 to 30, my VI is going to be 0, and therefore, and then I'm also going to start from 0 to 70, which allows me to just use this function twice. So if you pay attention here, VI got canceled out. I just carry VF squared equals 2A delta X down. My A is 2. The first delta X is 30 because I want to go from 0 to 30. And then my second delta X on this side is 70. So I'm really doing the same step twice. Why? Because it wants it between 30 to 70. So if you simplify all this stuff, VF squared on the left side here is going to equal to, 120. 2 times 2 is 4. 4 times 30 is 120. And then the right side, 2 times 2 is 4. 4 times 70 is 280. And then to get VF, we square root both sides. So the square root of 120, and then we have the square root of 280. Square root of 120 is about 10.95, and then the square root of 280 is about 16.73. So that is now my VI and VF, okay? So again, the VF here is now my initial as I'm doing it from 30 to 70. And then I know this velocity here, which is VF, so I know how fast these two or the car is moving at these two locations. So by the time the car gets to a position of 30 meters, it is moving at a rate of 10.95. It keeps getting faster and faster and faster and faster and faster. By the time it gets to the 70 meter mark, it is now moving at a rate of 16.73. So this is my initial, that's my final, which I just found. I'm going to add those two values. That will give me 27.68 in the numerator. I'm just going to carry the 2 in the denominator down. So therefore, the average velocity will be 13.84 meters per second. But again, it asks for average speed, so I'm just going to leave that as my answer. I don't need to include direction, okay? All right, the other way to do average speed is apply delta x over delta t. Here, we already know what delta x is. Delta x is 40. It's positive 40 because we're going to go from 30 to 70, which is a difference of 40. I don't know how much time it takes, though, okay? I don't know how much time it took for the car to keep accelerating from 30 to 70, but that's okay. We can just find it really quick. Well, one, you can use your displacement function from 0 to 30, and then you can use your displacement function again from 0 to 70. If you choose to do from 0 to 30, your VI is 0, so I just went and crossed that out. And therefore, we just do this twice. Okay, so from 0 to 30, I know my function is this. Delta x is 30, and then the acceleration is 2. The only thing that's left unknown here is my t squared. And then I can do this again for 0 to 70. But here, if I'm going to go from 0 to 70, my delta x is 70. And then the 1/2 a t squared stays the same on the right. Okay. Therefore, I can cross the 1/2 and the 2 here. The only missing terms in both these lines is the t squared. So therefore, on the left side here, we have t squared is equal to 30. And then on the right side, we have t squared is equal to 70. Square root both sides for each of these functions. Okay. Therefore, this, excuse me, made a mistake here. I forgot to take out the square. Excuse me, let me fix that real quick. Okay. Bam, let me fix that real quick. Oh, no, not the whole thing. I just need to erase the t, okay? Okay, so therefore, as I was saying, my bad, okay, so the square root, right, of 30 is about 5.48, and then on the right side, the square root of 70 is about 8.37. Now, if we take the difference in those two times, it will give us a value of about 2.89 seconds. So that's going to be our delta t. Okay, so it takes about 2.89 seconds for the car to go from 30 to 70. All right, so that's not too bad. Therefore, we can just substitute that in for delta t over here. So delta t is 2.89, and if we simplify this, 40 divided by 2.89 in your calculator, you'll get the same answer. Okay, so again, there are different strategies in terms of how to attack these types of problems, but it's good to start with fundamental kinematics equation, as I've done, and then hopefully just kind of find what you're missing correctly. All right, I hope that helps. Stay nerdy, don't be whack.